So it is about asymmetric curved non-commutative torus. And for me, I mean by a non-commutative Riemannian spin geometry, for me space will be an algebra, and type of this space will be type of the algebra, and metric and spin, Riemannian spin space will be described by a spectral triple. So in this sense, I'm very orthodox, conservative, as defined by Alan Kohn. So this is a triple of subalgebra of bounded operators, star subalgebra of bounded operators on some Hilbert space H, self-adjoint, compact resolvent, usually unbounded, certainly unbounded operator, okay, on an infinite dimensional Hilbert space, usually. And this absolutely, I will always here assume that the Dirac operator has bounded commutators with any element of the algebra. We think of the algebra as functions on the space D as a Dirac operator. You will see in a second, of course, the classical example, plus possibly more structures and conditions according to the task we will want to perform. Okay? So with such spectral triples, one can do a lot of tasks with additional structures. Just to mention, define classes in KK homology, extracting the topology, coupled to gauge fields, which was a very important theme of this workshop. So fluctuate such spectral triples, and write, minimize various interesting functionals and a lot of more. Not all of them can be done for so-called twisted spectral triples, for which the only difference is, well, there are various modifications possible, but that there are not commutators, but twisted commutators, twisted with some automorphism of the algebra. Okay. They will appear here, but I won't use them. Okay, so I will work. I'm staying in the framework of usual bounded commutators. Also, just to stay for this one well-demarcated class, I consider only the usual spectral triples, not spectral triples. Okay. So prototype, as you know, so classical spin manifolds, of course, an example of such spectral triples. In this case, the algebra is smooth functions, can be taken as smooth functions on the manifold, square integral spinor, sections of a spinor bundle. L2 with respect to the volume defined by the metric G, okay, so in coordinates is square root G dx, and the usual Dirac operator defined with respect to some spin structure. There is, in this case, reconstruction theorem under certain additional assumptions. Many, but there are not really abundant number of non-commutative examples, and they are often isolated. They come from foliations, non-commutative tori, which will be the main example here, finite algebras, quantum groups, Moyal plane. But part of a program which this fits is to elaborate methods to construct not just singular, individual examples, but to construct rich families, or much as possible families, ideally all, in some sense, of reasonable spectral triples on a given algebra A, and intrinsic, which means non-commutative analogs of some usual pertinent notions. And what are the reasonable spectral triples depends on which notions you would like to have on this spectral triple, and some of them will appear here, okay? So, not all classical notions we know from usual Riemannian spin geometry make sense, but many don't make sense, okay? For instance, we can define distance of states by supremum over this particular this set of difference of the values, absolute values of the states evaluated over element of the algebra. And if state is coming from a point, is a pure state, this is just distance of points. We have also possibility under some some assumptions to define at least first coefficients of the heat kernel expansion, asymptotic heat kernel expansion, which in the classical case goes like that for manifolds without boundary, compact manifolds without boundary, okay, where D is dimension of the manifold. Or equivalently, one can consider various special values or residues of the corresponding zeta functions, or non-commutative integral. In dimension 2, for instance, the main point of my interest, this functional, this notion, is the residue of the zeta function defined with the square of the Dirac operator, which classically is proportional with non-zero constant proportionality to the integral with the measure of the scalar curvature, and as a function of linear in f, function f, where R is the scalar curvature. Okay? In particular case of the non-commutative torus, which is, as an algebra, smooth algebra, is just Schwarz series in two generators with these commutation rules, theta is a real parameter. For many years, there was just one flat spectral triple. It's already 34 years. It has been introduced by Kohn in 80s in French book, which consists of, there is a sense to, okay, so they are precisely, this algebra is precisely such series of elements, of monomials, okay? There is also a usual trace with respect to which you can define L2 functions, L2 elements, square integrable elements, complete the algebra with these square integrable elements. And the only modification in 2 dimensions is you tensor this with 2-component complex space, like we usually like to have Dirac spinors in 2 dimensions. And the Dirac operator was very flat, was 2 derivations, which are also present in the non-commutative torus, well, with coefficients which are so-called 2 far-first Pauli matrices. So you can view this as matrix operator with derivations as matrix elements, okay? Investigation of, so it took several years, and first curved torus, this study was initiated in a paper by Kohn and Paula Cohen in 93, by employing, well, actually, essentially, when you strictly speak, it's not just such a, why it doesn't work, okay. There should be k to the power projection on the positive chirality spinors, actually, when one looks at the formula of this operator. Well, let me write it for simplicity like that, okay. So dressed Dirac, the dressed flat Dirac operator with k positive function, positive element, which are called conformally rescaled D, okay, and the related Laplacian. And it took some years to extract interesting geometry from it, okay, so to manage to compute this particular example of curved Dirac operator, which was the analog of Gauss-Bonnet theorem, so vanishing of the integrated scalar curvature of the zeta function in this particular case, which was done first in, always by the same authors, but called now Kohn and Paula Tretkov. Okay? And for arbitrary conformal class, it was done by Fatizadeh and Kalkani. And identification and computation in these papers of Kohn-Moscovici and also the same authors independently of the scalar curvature itself, not just integrated by the scalar curvature. Well, we shall see that it's not really scalar curvature, but a slightly dressed scalar curvature, as you expect. Well, dressed by the square root of G, essentially. And in the same paper of Kohn-Moscovici, actually, it's the proof of the vanishing of the zero value of this corresponding zeta function was simplified and made more conceptual, actually, because it has to be constant, this value has to be constant on all families of the type where S is a parameter, okay, and for T bounded self-adjoint operator. So in particular, for this conformally transformed Dirac operator. Well, methods were computational calculus, developed on. Well, no. I mean, it's true for this particular deformation. Our will be not of that. Okay, our will be not of that type. So methods, two-dimensional calculus, small time asymptotic assumption of the heat kernel, and all these computations were actually computer assisted. So there were several terms coming in the computations which were hard to, well, in principle one could do this, but they are simply, one has to, it's better to use the assistance of a computer. Well, this was spectacular achievement, this computation. And for that reason, I consider this triple to be very interesting. We can do some nice geometrics, get some nice results like that. But it is a twisted spectral triple. If K is not is element of the from the algebra, K no longer commutes with, has no longer bounded commutators with the elements of the algebra. To remain in the framework of spectral, usual spectral triples, we have with Andrzej an alternative for that. For instance, I briefly recall this paper, which is published in Journal of Mathematical Physics, in which we take the flat Dirac operator and add a term to it, so perturb, as physicists would say, by term like that. Okay, so this looks classically as most, well, at least most general metric here, coefficients in the first perturbation. One can put here arbitrary function, which classically means vier bind, or two binds in this case. So matrix mu and j run from 1 to 2 of coefficients, which mix the sigma indices and derivations, plus Hermitian conjugate operator. But we take this perturbation from the j, a, j. On the non-commutative torus, we are happy to have also real or non-commutative torus satisfies all these properties, additional properties of cone. In particular, there's also a real structure which takes by a joint action to the commutant of the algebra A. Okay?
Is it more likely having the magnetic field on the torus or the curved torus?
Well, we shall see it is a curved torus. Yeah, so it is not adding to gauge potential. Okay. On the top. Yes, well, it's a metric, it's a new metric. Yeah, this will be curved torus, okay? I'm coming in a second. It's, yes. I will speak about another one. This looks like most general, which may include, in higher dimensions, may include torsion and other pieces, which I cannot even give a name. But in 2 dimensions, we expect there is no torsion, at least of some type, okay? At least that one which doesn't capture spin-offs. So it is modification of the metric and the corresponding Dirac operator. In the commutant. I mean, it commutes with elements of the algebra. It's out of the algebra. It's in another piece of the algebra, which commutatively means the same algebra, okay? But non-commutatively, we have 2. If we have real structure, we have always 2 algebras, which are very, very nice. So it's more symmetric in a sense. By the way, if you do fluctuations with real structure J, you also use this other piece, okay? So that's, we heard this in the lecture of Balter and other lectures, okay? So, there are usual spectral triples. We can do, on top of them, usual fluctuations, for instance. We don't know if they are conformally flat because we don't know what is the meaning of the notion of to be conformally flat. Actually, okay. Let's say that classically, of course, any metric, any Dirac operator comes from some conformally flat metric for some conformal class tau. But on the quantum level, on the non-commutative level, it's not clear at all. There are more general families. For instance, we could also take this perturbation piece from the algebra generated by the algebra and the J itself. But then We are no longer in the class of usual spectral triples. Okay? We are not even in the class of twisted by some automorphic spectral triples. So completely new word. Outcome of this was, again, Gauss-Bonnet is very robust. It works also in this case, but we computed it only perturbatively. We managed to compute only perturbatively up to order 2 in the, so let's say, called small, formal, actually, perturbation in the coefficient epsilon. Okay? Yeah, it's normal. I mean, you can skip this. I mean, you can, keep just linear and quadratic terms in the perturbation in H. Okay. I call it small. Yeah, usual Dirac plus this operator, absolutely. Well, perturbative computations are more common than exact computations in physics, as you know, perhaps. And in this particular context, actually, I just learned last week they were present already in this paper of Vasilievich from 2005, okay, but not for non-commutative setup, okay? So we thought it's something due to, I propose it, this is a new stuff to look on perturbatively on this problem, but it is actually already known, okay? Well, when I told this to Alan Cohn, he was not particularly excited by it. He said, well, such perturbations should give trivial stuff. And also, okay, all our paper was to give exact computation and explain it where it comes. So, well, we shall see. Methods are same as for in the previous papers of Cohn, Moscovici, Fatizadeh, and it's same kind of methods, which we shall see in a moment. And I will report now another paper, just this preprint on the fresh preprint on the archive, in which we again establish the Gauss-Bonnet theorem, compute this combination, quantum analog of this square root determinant G are exactly this time, not perturbatively, but for a subfamily of perturbations, which just to make differently from the conformal rescalings, we do this in an asymmetric way. Namely, instead of multiplying from both sides the Dirac operator by some operator, okay, or some function, positive function raised to projection on the positive, raised to positive chiral projection, we modify only part of a Dirac operator. Again, we could, in principle, take K in this large algebra. Again, it wouldn't be usual spectral triple. Such perturbation, which I will describe in a second explicitly, were already or arose from a paper we had with Andrzej Communications 2 years ago, in which the Dirac operators on principal torus bundles, or circle bundle in this particular paper, and the later on principal torus bundles was discussed. And from a Dirac operator on a base and a principal connection on a non-commutative would be bounded, we will manage to produce Dirac operator on the top, which will be of the type which I will see in a moment, okay? And vice versa, when using Dirac, particular kind of Dirac invariant Dirac operator, which projects downstairs on the total space of a principal U1 or torus bundle, one can extract a Dirac operator on the manifold, on the base, and also principal connection on the principal fiber bundle. Strong connection in this sense. Strong connection in this sense, as defined by Hayat, okay, many years ago. This is possible. This computation is possible, and perhaps also more complicated computations are possible due to very recent and neat generalization by Lesch of so-called rearrangement lemma, which we shall see, which is important tool in the Kohn-Tretkov paper and also in other papers. Okay? So let's take classically asymmetric torus. So coordinates from 0 to 2 pi. Metric has coefficient in front of dy squared, where k is positive function of x and y. For instance, the usual embedding of 2T2 in R3, which is given by this particular prescription, okay, has the induced metric, which corresponds to k inverse or k1 over c plus cosine y. Okay? And it is this on the left-hand side. Okay? You see that these circles are, of course, smaller in the induced metric, in the metric of R3 than the circle is external surface. It's clear. So it is like that. In principle, this k can depend also on x, and then, well, that's the artist image of the embedded torus with k, which depends on x and y, okay? Which is Andrzej Sita's drawing, okay? Can compute classically the usual scalar curvature, and it comes like that. So there is only dependence of on k, which contains the derivatives in the x direction, because we took it like that, okay? Square, second, and first squared with coefficients like that. So there is also canonical Dirac operator for that metric. This is, of course, so one computes as one wants, spin connections or so on, or whatever, or just write 2-bind or normal 2-bind for that metric and easily guesses that it must, spin connection must look like that, and the Dirac operator, canonical Dirac operator looks like that. But it acts on this space with this measure, so square root determinant of G, okay, which is K inverse in this case. It's better to pass to one and same Hilbert space just by multiplying by square root of K, okay? This kills this measure factor, but transforms a little bit the explicit form of this Dirac operator, such one. So it looks similarly, except, well, this derivative jumped to y instead of x, okay? No, now this, on my previous slide, yeah, this was this picture, but this is x and y dependent. Yes, I'm interested in general situation. Okay, function which depends on two arguments. Okay. So on one and the same for any k, it acts on the same Hilbert space like that, with the measure coming from the Lebesgue measure coming from the coordinates, and has such a form classically. Okay. On the non-commutative torus, we take it like that, exactly like that. The only change, so we change the Hilbert space. Instead of the integration with the measure, we take non-commutative trace. And instead of the derivatives, we take I times the derivations, which are present here. So the operator looks similarly. There are no I's there because they are hidden in the, they were anti-Hermitian, so they are, these are Hermitian derivations after I the anti-Hermitian derivations. Dirac operator looks like that. So this is my non-commutative Dirac operator, and it acts on Hilbert space of square integrable elements or completion of the Schwarz elements, Schwarz functions with the trace, with the scalar product defined by the trace. So K is in the commutant. The computations you can do also for not being commutant, but I want to stay in the usual spherical triplet, so K is in the commutant. Here, for me, it's K in the commutant. But the computation actually, the explicit computations change a little bit, but strictly they are going in similar way. Similar difficulty, let's say. They are not easier here. So we regard now this zeta function of square of this operator at 0 as, well, 4 pi square t, because t is actually 1 over 4 pi square usual integral, double integral with these coordinates from 0 to 2 pi, okay? Evaluated on quantum analog of something which I would like to call, quantum analog of K inverse R. But K inverse R classically you can write also as R K inverse or any other way as you like, but not in the quantum way, and not in the non-commutative way when there is no preferred order of these terms. Okay, K doesn't commute with R in general, okay? So let me say, we are really computing quantum analog of that. There is no way to extract this R separately, okay? from the formula. That's just to make it really, to make it short. So this analog can be something like that or something more complicated. We don't know what is it. So some computation gives us some quantum analog of K inverse R. Okay, that's what I said. Well, R will be also from the commutant. Okay, so this doesn't commute with K. R will be from the commutant. We will see explicit formula in a moment. So the scalar, K inverse scalar curvature as we compute will be from the commutant. So now there is D is actually differential operator in sense of Kohn, and one can follow Kohn, Tretkov, Kohn-Moscovici, and the other computations by Kali, Fatizadeh, which were already done, and compute this zeta function 0 of the square of this Dirac operator by symbol calculus with peculiarities in dimension 2. So the first step is to compute square of the Dirac operator. It has this number of terms. Okay. The second order pieces are here. They should. The symbol has three pieces: second order, first order, and 0 order. Okay. The next step is that it was shown by Kohn-Tretkov already, that this zeta function can be computed as minus the integral over the covariables, okay, covectors, xi, of the trace of symbol of order -4 of the pseudo-differential operator d square plus 1, inverse of the d square plus 1. So one has to be careful with this computation. Keep this 1 as 1 of symbol 2, order 2, and so on, so on. But the pseudo-differential calculus, which is usual pseudo-differential calculus in which the first slot you take the derivatives with respect to the covectors xi1, xi2, and the other slot you take the derivations, d1, d2, the usual formula, produce the recursive formula for this coefficient b2 in terms of a coefficient b1 and coefficient b0, which is just inverse of this function a2. A2 was this symbol of order 2 was just, so b0 is 1 over that particular function. Okay? So it looks simple, but there are several terms here. Several terms because in each going order, going up to b2, they multiply several times. And explicitly, I will list for you only those terms which have positive, which have even powers in xi1 and xi2. There are even more of general terms. But we still have to do integration over the xi, so I omit completely any term which has odd power of xi1 or xi2. Okay? So then this b2 coefficient as a function of zeta1 and zeta2 has three pieces. First piece looks like that. So the formula are quite different from this, which you have and others, but at the end, B, second piece. Okay, so you see these pieces are grouped in the first one. There are L1 derivatives, first derivative with respect to the first derivation of K. The second piece, I collected second derivations of K, and here they are higher. First times, 2 times second derivative with respect to first variable, and so on. So a lot of terms, and it's very difficult to integrate this with respect to xi1, xi2 in principle. And also then compute trace on this object. But at least at this point, we can check the classical value that we are okay. So for theta equals 0, there are some commutation relations, so you can reshuffle the terms and combine them into this expression. Okay, b2 looks like classic like that. And miracle after integration over xi1, xi2, which was done, I think, by computer first. I don't know. One gets very nice formula like that, which, after applying trace to this formula, produces 1 over 48 pi K inverse R, where R is this expression I gave you a few transparencies back, classically computed R. Okay? So perfectly matches the classical scalar curvature, as well as the coefficient, because this coefficient is slightly different from the coefficient from the Laplacian. And also there is this 1 over 4 pi square coming from the fact that tau is classically, this trace classically is in these coordinates 1 over 4 pi square. But it perfectly matches the result. So now the integration over, well, we would like to tackle the integration over xi1 and xi2, zeta1, zeta2, or actually the xi1, xi2. And there is a formulation or another proof and better presentation of a result of this rearrangement lemma, which was present for particular functions in the papers of Alan and Oyors one. Okay, this works for general class or for large class of functions. Okay, so anytime we'll want to compute the integral, which has, well, some functions up to p, we will need only 2, up to p equal 2, formula for p equal 2 at most, of a non-commutative variable k, same variable k, times u. U is just usual number from 0. We integrate over u from 0 to infinity. And b1, b2, bp are other elements which do not necessarily, they don't commute with k. Okay? Well, one can reshuffle, demonstrate and show, nice paper by Lesch, that, well, I presented slightly with slightly changed coordinates. I think the k square in the paper of Lesch and so on. So one can write it as, well, up to k inverse square root, as certain function f of p variables, evaluated on, well, delta 1 is this modular transformation, which is k acting as adjoint with k inverse on any element, okay? But this index 1 tells you that you acted on first element here. Well, this is slightly misleading. One doesn't know if it really makes sense because one can write product of these guys in different ways. But, I mean, writing in one way, actually Lesch proves this theorem by inserting in tensor product, so splitting, polarizing this formula and so on. But at the end, for written them, if they stand like that, one writes them in same order in this, as such a product, and then delta 1 acts on b1. On delta, then this second, s as a function of the second element, you substitute here this modular automorphism applied to the first b1 and modular automorphism applied to the second b2, and so on up to 3. It's quite completed formula, where function f has very simple expression. It's just integral over du of this f0 up to fp functions of one in the same variable. Okay, so one takes this product of these functions at first u, then u times s1, sp, and this function f as a function of p values from s1 to sp has such a form. Okay? So this I already explained that this is adjoint by k inverse operation acting on jth element of this product. Well, we need such integrals in our case. Okay, so our expression contains integrals of the type. Okay, over xi1, xi2, of expression at most 2 guys here. There were just derivations of k, derivatives of k in various combinations. Some powers of k collected, some powers of xi1, xi2, possibly standing outside. And b0 is entering with some powers also m1, m2, m3 of this one, of the inverse of the principal symbol of the Dirac, of the square of the Dirac operator. So after, slight adaptation of the formula by Lesch, we get the following result. that this j, same j, which we have to compute, is f of two variables with evaluated on the first modular and product of modular transformation, the first variable and the second variable, on this x and y, which we see in this integral we have to perform, okay? Here. Where, and that's the main point, this function f as a function of two variables is a double integral in this case because we have double integral here, okay? Of over dv and du from 0 to infinity. Coefficient 2 comes because, well, we had from minus infinity to infinity integral, okay? And some power of k, and this expression, fractional expression, which is quite different, I think, from this which you get in other case of the conformal rescaling Dirac operator. It's even simpler, but of that type. Okay, so you see all these powers coming here, and we see the particular fractions. So s to some power over that, t to some power over that, monomial. And this function, as in the case of Lesch in general, I mean, has the property that when y is 1, okay, when this collapses, you can collapse this to 1 point, a function of one variable, okay? So in case if y is 1, and f depends only on one variable and has the same definition, okay? So now one should apply also this trace to this expression like that, so to expressions like that, okay? I'm not sure we really use it. I think it's universal formula for this particular. So they are quite different, but okay. So now there is a nice lemma observation. Then when you apply the trace to such a formula, okay. So remember, this was action by modular. I mean, this by adjoint action by K inverse. So there are a lot of identities for functionals like a trace, okay. So one can. X and y are guys which you see in the integral we have to compute. So in this concrete case, in the formula we have here, they are like this. This is like x here, and this is y. But okay, well, the rest, I mean, this all this is they are derivations. Derivation of k need not to commute with k itself. So you should treat this as something. I'm not sure. I know Harald knows a lot of operator formulas, and I learned from Harald in the ST7. I'm not sure this Lesch or previous rearrangement lemma was discovered by physicists earlier. I'm not quite sure. But anyway, it's a tool which we use here. Okay. So taking trace amounts on such expression which we have actually, okay, to compute, to evaluate this second variable just to identity, okay, turns out, on a product, which in turn is the same thing as, well, substituting just one, so as a first function of one variable only, okay, applied to x and then multiplied by y. So these are some identities, operatorial identities. And in case of one variable like that. And this can be computed by just applying to monomials of that type. So explicitly to convince oneself that this works. And now comes the main result, main computation, okay? So the dressed scalar curvature, so quantum analog of this expression, okay, for this asymmetric torus, for the Dirac operator as I defined before, has this form, okay? So there are 5 functions of first derivatives of k of one function of one variable of the square of the first derivative, function of second derivative of k, function of second derivative of k, and function. There is no function of second derivative of k. So this, as part of the result is that you don't see it, okay? It's 0, so as a part of the result, there should be also f2 here evaluated on delta del 2 of k, but claim 0, okay? Where f11, the integration is this particular function, again a fractional function of 2 variables s and t, quite complicated but not terribly complicated like logarithms in your case, okay? Well, we have to integrate, well, s and t we need only for positive values, okay, from 0 to infinity. So there are no poles on positive s and t. Okay. So just this particular form of the function of one variable g1, function g2, f22, and f1. And the claim is, which is, okay, the statement of Gauss-Bonnet, that trace of this expression vanishes. It's still not clear that it vanishes. And also here we wanted to understand it more conceptual way. So first of all, one looks on this part, okay, and just explicitly see that inserting 1 in f22 plus g2 produces a function just which is 0. Okay. Instead, f22 evaluated, okay, f2, which is not present here, or I mean, I should write here f2 of del 2 of k, and f2 is 0, okay. So I didn't write it, but one gets explicitly also that this function vanishes under the trace. So all terms which contain second derivative of k vanish, okay. Then there are terms of with the first derivatives of k, and first looking on f11 under the trace of 1 plus g1, so the first, this sum, okay, it gets this particular form. So one can make it in common denominator and obtain such a function when evaluated at 1. Then using some Leibniz rule, invariance of t gets the following expression. Okay. And then all the terms which contain this first derivative of k, which this tree can be written in this way, where there is one function h of one variable only, it's like that, okay? So at the end, all this controlled by such a function, making it to the common denominator. Now, this function is still, it's not clear why this should be 0, okay? So now there is a few identities. So this expression, this function h evaluated, I mean, we need to compute at the end that this is 0, okay? We want to show this is 0, where h is a function which combines all these f11, j1, f2 into such a way, okay? Combination of all these three under the trace gives this function. Now there is an observation that for NAB, again, because of the properties of t, this which we want to compute can be written in such a way. Okay, well, there is third power of this modular automorphism here, but okay, A and B. And also it can be written in such a way, okay? So these two things must be equal for any A and B. But for A equal B, this is h of delta delta cube, which is this as a function of s. Okay? And right-hand side, which should be equal for a equal b, is this. And both, I mean this, which is minus this. So both these two expressions actually for a equal b are of opposite sign. They are just opposite. So both must be 0. And this shows that overall trace of this expression vanishes. This is explanation why it vanishes. You see it, this is 0, but that's explanation. So the Gauss-Bonnet theorem holds. Okay. So let me pass to two just last transparencies, conclusions. So we have introduced a new class of Dirac operators on non-commutative torus, which define a new class of usual spectral triples and shown the Gauss-Bonnet theorem, and computed also established the formula for the dressed scalar curvature. We employed the algebra JAJ, commutative with A, and which now can be perturbed by the usual fluctuations, so adding gauge fields, which is not clear, I think, which forms one should use for the twisted spectral triples. So that's next computation should be to also perturb in this way. And of course, they define also classes in the usual, I mean, the cyclic, not twisted, cyclic cohomology. For that, we had to start with a real structure, so operator J, which goes to the commutant, antilinear transformation. I don't know. Okay, one can start perhaps with something which has commutant. Okay, one can start with some that there is a commutant. Okay, one can start without J. We started with J here, but this J survives because we are staying always on the same Hilbert space, but it no longer satisfies other properties like first order condition with the perturbed spectral triple, or the cohomology dimension, K-O dimension, and things like that. So we can start with it. It still is there. It goes to commutant, but it doesn't fulfill other additional structures one would possibly could put on this spectral triple. Of course, let me stress this again, even though classical limit of any metric conformally flat, here we are completely not sure about that. I don't know if they are different, and even if they, in commutative case, so for theta 0 produce the same metric, they may be different expressions. They may be different quantum operators in principle. Because of this dressed character of the scalar curvature, actually we are going to compare it with Rosenberg paper, recent paper in which he computed completely differently. It got different expressions, but who knows, maybe it is just the artifact of this dressing. Or computation we heard here by in coordinates, okay, special coordinates. So why not compute it if it matches the computation in particular coordinates, so embedding this non-commutative torus into usual space. We plan to generalize this higher dimension, and in particular study this case of this communications paper with Andrzej. We studied the curvature minimality of these Dirac operators on this paper, which, by the way, I should also perhaps say nowadays, one of the first examples of an unbounded spectral triple on a non-trivial, non-commutative bundle, which should fit somehow to K-Hilbert modules approach, which recently is very popular, and we heard about it already during this conference. Open questions. I don't know how this D is related, if any, if at all, to some rescaling in the sense of con of the usual flat Dirac operator. What does it mean, conformal equivalence in that case? I don't know what are the admissive spectral triples on non-commutative torus. Is our reason of spectral triple is the rescaling perturbation reason of spectral theory, at least from the point of view of Gauss-Bonnet theorem. They seem to give a nice, they behave properly. I mean, we can say something about Gauss-Bonnet theorem. Actually, we can control it, and actually it holds, okay? So for instance, all these expressions will define the same metric, but we don't know if among them or other classes we define the same metric is one which is minimizes something, like torsion or other pieces, like so analog of the usual canonical spectral clip in the commutative situation. Can the torsion be, or at least the condition that torsion is zero, which is usually simpler to be defined, can be separately defined, or it mixes with the scalar curvature and so on. So all these questions are questions which I'm personally interested. Andre is also interested, and everybody who is interested, we are ready to discuss. And which method of? Well, we don't know what is the connection here. Okay? Connection doesn't make sense so far. Okay. Well, yeah, but minimize of under connection, but we don't know what are connections. So one can minimize the Einstein-Hilbert action in